Thanks very much for the opportunity to speak to you today. I'm really excited to share work that I've been doing with a great team on a new type of space telescope, a Megaconstellation telescope. So let me start by talking a little bit about how astronomers look at the sky and the tools that we use to do that. So this image here, this very thin slice, is our galaxy, our home galaxy, in optical light, in visible light that we can see with our eyes. So for most of human history, this is how we have looked at the universe. This little sliver with sort of dusty bits and pieces covering up the center of the galaxy. But in modern times, we've built sort of auxiliary eyes, detectors that can see other parts of the electromagnetic spectrum. So here you see various pieces of the infrared spectrum. So in infrared, you can actually see straight through that dusty stuff that covers up the center of the galaxy in optical, and you can see right through to the center. So we have a different view on our universe with different detectors. And we've continued to do this as technology has progressed. We have moved to radio. You can see the galaxy here in two different wavelengths of radio. And we've built bigger and bigger telescopes on the ground and in space to look at different parts of the radio spectrum. We've done the same at the high energy end of the spectrum. This is X-ray light and also gamma ray. And so combined, we have a multispectral view of our galaxy, of the universe. At different wavelengths, you can see different features that tell us about different physical processes happening in the universe, from supernovas through star formation and everything in between. There is a piece of this picture, however, that is missing. And that's going to be what I spend most of this presentation talking about. So this is another way of showing the same thing. You can see that we have wavelength, which is the energy of electromagnetic radiation on the horizontal axis, and atmospheric opacity, which is how clear or not clear the atmosphere is to that particular wavelength. So high energy waves like gamma rays, X-rays, and ultraviolet, they don't go through the atmosphere, which is good for us. But we've had to build space telescopes in order to see the universe in those wavelengths. Visible light does go through the atmosphere, which is good. We can use it to see with our eyes. Near infrared as well, but far infrared does not. And so we've built telescopes like the James Webb Space Telescope to look at the universe in far infrared, and it's returned some truly stunning images of our galaxy and other galaxies as well. Radio waves do come through the atmosphere for most of the radio spectrum, and so we have wonderful ground-based telescopes to observe the radio universe, except at the very far end of the radio spectrum. Down below about 10 megahertz, we can no longer see through the Earth's atmosphere out into the universe. And so that part of the spectrum is missing. It's missing from our understanding of the universe. We can't see below about 10 megahertz from the ground, unfortunately. And so when I learned about this really early in my career, that really bothered me. I love the multi-wavelength picture of our galaxy and the universe that I just showed, but I want it to be complete. And so that was the inspiration for developing GOLO. This is the best map we have of the universe at long wavelengths. This is 3.93 megahertz and 6.55 megahertz. These are contour maps, and these were developed using the RAE-2 spacecraft in the 1970s. So these maps were a real accomplishment at the time with the spacecraft and the technology that was available, but we haven't really done much better since. This is what we have for low frequencies. It's a far cry from the beautiful detailed maps that I showed you a few slides ago, but this is all we have, and this is all we've had for 50 years. And so I really want to change this. And so I've decided to spend, a good chunk of my career trying to change this and give us a better view of the universe at long wavelengths, at low frequencies. So that's what GOLO is all about. GOLO is a great observatory like Hubble, like James Webb, except for long wavelengths. So the idea is that we want to build a constellation telescope, a free-flying, space-based interferometric constellation that is massively redundant and upgradable, very different from something like James Webb. And it's located far from the Earth to be away from noise and interference. And we're designing this to look at exoplanets. Exoplanets are really one of the most, in my opinion, my biased opinion, exciting astronomical developments of the last 20 or 30 years. The proliferation of exoplanets and all the things that we can learn about them has been really exciting, both for scientists and I think for everyone in the public, that we can learn about other planets for real. So that's what GOLO is focused on. I'm going to let my colleague Melody Cow tell you a little bit more about the science that we can do with GOLO for exoplanets.
So the question is, why haven't we built a space telescope to explore this part of the spectrum? It's because a telescope must be many wavelengths across to provide resolution. So a telescope that observes waves tens of meters to kilometers long must be hundreds of meters to many kilometers across. GOLO is an array of spacecraft spanning thousands of kilometers. With GOLO, we'll finally be able to see the low-frequency sky in fine detail. And what will we see? Exoplanets in the solar neighborhood, blinking on and off with radio aurora from their magnetic fields, interacting with stellar winds like fireflies in the dark. These radio aurora carry important information about their planets, whether or not the planet has a magnetic field, how strong it is, how fast the planet is rotating, and even hints about what's inside each planet. Studying exoplanet radio aurora and the magnetic fields that they trace is an important piece of the habitability puzzle, and it's a key science goal for GOLO.
So this is what we're focused on, exoplanets, learning about planets in our solar neighborhood that might be like Earth, that maybe have living things on them. So, sorry. Advance my slides. Stand by. There we go. So I have been working with a fantastic but small team to look at how could we build a telescope like this? How can we build GOLO? How can we build this Megaconstellation telescope? And that's been the focus of a NASA NIAC phase 1 study. NIAC is NASA's kind of crazy ideas, but plausible ideas line of funding. So the first question we asked was, where should we put GOLO? Where should it be in space? And what we've settled on are the Earth-Sun L4 or L5 Lagrange points. These are special places in space where the gravitational potential of the sun and the Earth kind of balance each other out. And so you have a special spot, either 60 degrees ahead of the Earth or 60 degrees behind the Earth, where you can put things and they'll pretty much stay there. So there's not a lot of propulsion needed to keep things in that location. It's far away from the Earth, which is good from the perspective of noise. We don't want noise in our telescope to mess up our observations. It's a little tricky for communications, but we think we have a solution for that. And importantly, putting things at these Lagrange points means that they won't come back and cause space debris problems for the Earth. So anything you put there will stay there stably for thousands of years. So we won't be contributing to the low Earth orbit space debris problem. So that's where we want to put GOLO. The next question is, what is the design? Sorry, my slides are getting ahead of me. So the design that we've come up with is a combination of many very small spacecraft. So these are loaf of bread sized spacecraft with a big antenna on them. These are what we call listener nodes. And they simply listen. They collect data with their antenna, and then they transmit it to larger spacecraft that are called communication and computation nodes, or CCN. And these are more like the size of a mini fridge, still not very big by spacecraft standards, but these have a little more capability, and they also have the ability to communicate with the Earth. So the way that it works is we have these listener nodes and these CCN. They're out in the universe. I'm hoping this animation will work. Yes, there we go. So they collect science data from exoplanets and other phenomena out in the universe. The data is then sent to the CCN, where onboard processing computers turn that into a much smaller data product, which then can be sent to the Earth via a laser link. So transmitting data over an optical link with light to the Earth. So there's a lot of benefits to a constellation telescope. The first is that you can use mass production, factory production, to make the spacecraft. And you can also build up the constellation piece by piece. You don't have to do one gigantic monolithic telescope like James Webb. You can build it up over time. You also can replace pieces when they fail. It's massively redundant in the sense that, you can lose a few spacecraft and you don't lose the functionality of the whole telescope. And finally, it's reconfigurable. You can move around the elements so that you can do different types of observations with the same components. So it's very flexible. I want to talk a little bit about the graduated growth to finish up. GOLO is unique in that you can start with a small version of it and it still can do really exciting science. This part of the spectrum is so unexplored that you don't need to start with the full-sized GOLO that I want to build eventually. You can start with maybe 10, a handful, 5 or 10 spacecraft, and you'll learn very exciting things about the sun and space weather and coronal mass ejections that get thrown at the Earth and other planets, as well as the other planets in the solar system. So that's with just a few antennas, a few spacecraft. Then as you grow the constellation to, say, 100, you can suddenly look at things like lightning on the gas giants in the solar system, Uranus and Neptune and Saturn and Jupiter. And we can start looking at cosmology. We can start looking back in cosmic time by looking at redshifted hydrogen, which makes up most of the universe. We can begin to look back at a time in the history of the universe when there were no stars, before stars had formed and turned on their fusion engines. It's called the Cosmic Dark Ages, and that's a really exciting thing that we can access with GOLO, even a small version of it. As you move up to more spacecraft, you're able to make better, higher resolution, higher sensitivity maps of the galaxy, of the universe, and really test the cosmological theory about this dark ages, this time with no stars, in detail that we simply can't do from the surface of the Earth. And then finally, when we move up to the full size, then we'll have the sensitivity to detect exoplanets, their magnetic fields, and potentially learn about whether they might be habitable. So we can grow this telescope over time. And what that means is, unlike single telescopes where it's just one physical thing, this is a telescope that could potentially be built up as a global collaborative enterprise. I deeply believe in exploration of space and science as a place where everyone in the world can come together. And my long-term vision, which is going to take some time to achieve, but my long-term vision is a collaboratively built space telescope where people all over the world can contribute. Anywhere that can build a spacecraft can send components to GOLO. So that is the long-term vision that I have. I want to finish by highlighting the wonderful team that I'm working with from all over the country. And thank you very much for your time. I think we do have a little bit of time for questions if there are any.